Okay, so today I want to just kind of wrap up the material for the semester, actually. So we'll wrap up worksheet 23, and then also want to just talk a little bit about what the plan is for the last couple weeks of class. So nice to see you all, or some of you. Hope you guys had a nice break, and let's just kind of feel like it's been a month rather than a week since we've seen each other. What's left for us is we have a final, well, not really, we have a third exam, which is scheduled for a week from today, exactly at this time. So our third exam will be Monday from 11, it's scheduled for 2 hours. So it's from 11 to 1 on December 7th, so the next week. It'll be the same as we've been doing it on Zoom, remotely with your cameras on. There'll be a multiple choice part, there'll be a written part. This exam is going to just really focus on chapter 6, what we've been doing with Laplace Transform. So it's not a comprehensive final, it's more like a third exam. Since there's less material on this one than the other two exams, this exam is worth also a little bit less. So it's worth, I think, like 12.5% of your overall grade. So just keep that in mind. So all that's remaining for you to do this semester in this class is submit your homework for tonight, which is due tonight, and then you've got your third exam on Monday. There's not going to be a reading assignment on Wednesday. So your exams have all been graded, so hopefully you've had a chance to look over those comments. Your homeworks, everything that you've submitted up to now has been graded as well, so feel free, if you have any questions about how the homeworks have been graded, please let me know. But your grades should all be updated, at least at this point, so you have some idea about where you stand, what you need to get on the final, and so on. If anybody has any questions or concerns about their standing in the class, and you're thinking about withdrawing or changing to a P+, PF policy, we can still do that up until, I think, Thursday or Friday. So please just let me know if you're curious about that. Any questions so far?
Professor, you said we could still change to a P or P+. I thought that deadline was far past.
That deadline was passed in the sense that for students to be able to do that without instructor approval, you can still make that change. It just requires your instructor to approve it. So for me, I'm happy to approve it for anybody. If you're thinking about this for another class, the instructor does have the discretion to allow you to do that or not. Okay, any other questions? And I just want to kind of take us over to the website. One thing that I really want to kindly ask you all to do, if you haven't done it, you don't have to do it right now, but I'll remind you at the end of class, is to complete the FCQs. You know, getting a good response rate, it really makes the data meaningful. So I'm hoping to get our response rate for the class up to about 80%. We're pretty far from that right now. I didn't want to bother you about it over the break, but I'm going to bother you about it now. So please, if you have some time today, fill out your FCQs for this class and all of your classes. Your feedback is definitely really valuable and important to me. So thanks for taking some time to do that if you've done it already, and please don't forget to do it if you haven't. Let's see, so otherwise, we're gonna wrap up material today. Your homework is due tonight, and I put up some review problems for the exam here just shortly, and I'll put up solutions to those shortly as well. And once your homework has been submitted, I'll put up an answer key for that so you could check your work while it's in the process of being graded. Okay, any questions about that plan? Okay, so I think that was any of the announcements that I wanted to start with. So let's pick up from where we left off, which was working with how we can use Laplace transforms to solve differential equations. And so this is what your homework is on. So we did a bunch of stuff for worksheet 23 last week, right before the break. So we were working on, this is worksheet 23, where basically we're using Laplace transforms to solve some initial value problems. So I believe we did A together, and then maybe we did 2 of these together, and then one of you guys worked on in groups. So just since it has been a little bit of time, maybe we can just start with a recap of how this goes, and then practice a little bit more. So really there's no new content that I'm going to present to you other than let's get some more practice with using Laplace transforms to solve differential equations. And with that in mind, I'll just say we'll wrap this up today. So Wednesday's class is just going to be we can just chat about the exam and go over any questions that you might have for that. So Wednesday's class will kind of be more of a open-ended problem session. So if you have some problems that you would like to discuss on Wednesday, definitely let me know. I figure we can talk about some of the homework that you have due tonight if you have any questions about that on Wednesday. Okay, so if we're going to solve a differential equation such as this one, so here we've got a second order differential equation, constant coefficients, and we have some initial conditions. And again, one really important point to make is if we don't have initial conditions, then we can't use this process. So this process works when we have initial conditions. So the process that we outlined was, okay, first, we're going to take the Laplace transform of both sides. So that's what that script L means. So on the left side, we use properties L1 and L2 to split up the sums and pull out the constants. And then on the right side, we refer to the table of Laplace transforms. So the entry of interest for us is, well, if I want to take the Laplace transform of this is the entry, that would make sense. My value for A is 1, and my value for N is also 1. So that's where this comes from over here. Okay, questions? Okay, so then we would use the properties for derivatives. That says, okay, when I take the Laplace transform of the second derivative of a function, then I get s squared times the Laplace transform of the function minus s times the value at 0 minus the value of the derivative at 0. We apply that derivative property for y prime. That gives us s times y of s minus y of 0. And and then we've got the Laplace transform of y we're denoting with capital Y. So when we use this notation, y of s, just be sure this is a capital Y, and it's not multiplying s, it's y is a function of s. So when you're doing these on homework, I will very kindly ask you to really check your work, because there's a lot of algebra in this process for anyone that's been going through it, and they can take some time. Questions 7, A, B, and C on your homework do take some time. So just go carefully and then double check things afterwards, just to make sure you're doing your algebra correctly. And so here, what we'd want to be careful about in particular is making sure that we distribute this 4 in through the second term there. Sorry, there's a delay on my iPad, I think. Okay. So, so next, after we Laplace transform everything, then we're going to solve for y of s, capital Y of s. In other words, we're going to find out what the Laplace transform of the solution looks like. So here's where the algebra comes in. So what we typically do is we group all of the terms that have a capital Y in them, like this one, this one, this one. We group them all in here. And then we group all of the terms that don't have a capital Y in them together. And another thing to just keep in mind is that we use these values here and here when we are plugging in things for y0 and y prime 0. Any questions? Okay, and so then the point of grouping all these terms together, these y terms, is that then we can factor it out below. And on the right side, what I'm going to do is write this sum as a single fraction. Since one thing that you'll probably have observed in solving these problems is it typically involves partial fraction decomposition or something like that. So rather than do it several different partial fraction decompositions, sometimes it's nicer to just have one fraction on the right side so that you only need to do one partial fraction decomposition. So that's why I grouped these two terms and kind of wrote them as a single fraction. Okay, and so then what I could do is divide both sides by the s squared plus 4s minus 5. And just keep in mind that this has a factor of s plus 5 and a factor of s minus 1. So that's where the s minus 1 cubed comes from. And so then once we get to this point, this is step 2. We've solved for capital Y of s. And hopefully you got my announcement yesterday, since some people had some problems with the last question on the homework 7C, that finding the inverse Laplace transform of that one is certainly possible. It's just involves quite a bit of algebra that is a little bit messy. So for the very last one on your homework 7C, you could just stop when you get to this point and you don't need to do the last step of finding the inverse Laplace transform. So for 7C, it's totally fine to just say, here's what capital Y is, and I'm not going to do this last step to figure out what lowercase y is. For parts A and B, you are expected to kind of go all the way through the process. Okay, so then for this one, after we've solved for y, we then can go ahead and take the inverse Laplace transform of it to then find the solution. So one thing that I want to point out here is we have a special case in that we have a repeated root in the denominator. And that's going to be the case for, I think, 7b or 7a. One of them has a couple of repeated roots as well. So when you're doing that partial fraction decomposition for a repeated root, we need to have every power of that root of that factor represented in our partial fraction decomposition, because you need to think about what are all of the fractions that we could add together that would give us something like this. Well, if we added all of these things together, the lowest common denominator would in fact be this. And when you're dealing with a repeated root, normally if our denominator is quadratic, right, the numerator has one power less. So when we have a linear denominator, our numerator is constant, like this and like this. When we have a quadratic denominator, we should technically have a linear numerator. So we should have like a CS plus D. But when you have this special case of repeated roots, then you only need a constant on the top. So this was kind of one of these special cases that's spelled out in the extra notes that you guys have about partial fraction decomposition. So if you're kind of curious about this, go back and check out the integration notes about partial fraction decomposition that kind of goes through some of these cases. But we now have 4 unknowns that we would need to solve for. I'm not going to go through that process because it takes a bit of time. That might not be the best use of our time together, but I'll put the solutions here for you. And then the big advantage for that is once we identify what each of these constants A, B, C, and D are, that means that then when I take the inverse Laplace transform of all of this stuff, right, the point of partial fraction decomposition is we can break up sums and differences. So if I can take this fraction and write it as a sum of a bunch of things that I can find the inverse Laplace transform of, then we're good to go. So this works very much the same way it works when we were doing like standard integration. So that means this inverse Laplace transform that we want to calculate, we can do this one plus this one plus this one plus that one. So that's what's going on down here, is I can pull out the constant A, and what's left to do is take the inverse Laplace transform of 1 over s plus 5. And then this one would be B times the inverse Laplace transform of 1 over s minus 1, and so on. And so now what's nice is each of these things in here, we can actually evaluate using the table of Laplace transforms, which gives us each of these values over here. So these last ones, calculating the inverse Laplace transform of this one and this one require us to use this rule that we had up here. So we're basically going the opposite way down here. So that was just kind of a walkthrough of this process. Any questions about that? Are there any questions that you guys came across in homework that seem like it might be a good place to ask here? Okay. So then let's take a look at problems in D and E on this worksheet. So these are going to be a little bit trickier now. We haven't solved anything that looks like this yet, where we now have t's in front of the y double prime and the y prime term. So this is now no longer constant coefficients. So just keep in mind, like with a problem like this, we couldn't use the set up the characteristic equation, find the homogeneous solution, so on, that process, because this doesn't work when we've got t's over here. So we're not going to kind of change much about how we do this. We just need to be more careful about how we use the properties when we take the Laplace transform of the left side. So I certainly can split up the sums just like we did before. Which gives us that. And again, we can't, well, sorry, there's like a slight delay here. Here we go. And we can't pull out those t's again. So what we need to use is this property, sorry to fly around, that we talked about last week, which is the very last one. So this property L5 over, oh, sorry, there's like a big lag in what I'm doing on my iPad. Here we are, okay. So we want to use this property L5, right, which tells us what to do when we take the Laplace transform of some power of t times some function f of t. So for us, I think we've got like t to the first power. Our value for n is 1. So I'll just say you haven't had one of these on homework. You didn't have to do one on homework that had these t's here. You very well may have to do something like this on the exam. So definitely be sure to give some of these a look. There's one on the practice sheet as well. So in this case, when we have a n is equal to 1, we have t to the first power up here, then that means this is equivalent to taking the derivative, first derivative of the Laplace transform of y double prime times minus 1 to the first power. Okay, and again, this is property L5. And we could do this same thing over here, which is this is going to be minus 1 to the first power times the derivative, first derivative of the Laplace transform of y prime. Okay, and then we take the Laplace transform of lowercase y, which we're just going to call it capital Y, and then we take the Laplace transform of 2. Any question?
So what we're working on is analogous to question 5 on the homework?
No, you don't have one on the homework that has these t's in it. On the review, are you looking at like the set of review problems? I don't think there was anything on the homework that had you to do something like this. I don't have the homework in front of me just yet.
No problem. Thank you, though.
Let me take a look. Sorry, my computer is some reason just slightly slow today. Let's slow from the break. So, okay, yeah. So in question 5, yeah, you'll have to use this property for one of them. That's right. Yeah, I see. Okay, so this means we've got this -1 to the n, which our n value is 1 since we have t to the first power, times the derivative of the Laplace transform of y double prime. So in place of this goes s squared, capital Y of s, minus s times y of 0 minus y prime of 0. I'll wait for my iPad to catch up. There it goes. Okay. So that's just using the same old formula for y Laplace transform of the second derivative. We haven't taken into account that we've multiplied that by t. So we still need to take the derivative of that with respect to s. And so now for the second piece, where we want to take the Laplace transform of t times y prime. Here we have a negative and a -1 to the first power, so that gives us the positive sign down below. But then we've got the derivative of the Laplace transform of y prime, which would be s times capital Y minus y lowercase y 0. Sorry, just giving my iPad a chance. Seems to be getting more of a lag as time is going on here. Okay, so sorry, what I was kind of saying, but you weren't seeing the writing was right this. Yeah, we still got a lag here, sorry. So the s times capital YS minus y of 0, this stuff, oh, here we go, comes from this over here. Then we have this ys over here, and we still have this on the 2 over s on the right side. And so now we're going to take the derivative of these things with respect to s. So now we're going to take into account the fact that we had a t to the first power there. So I take the derivative of this expression here with respect to s. So s is my variable. So for this thing over here, we need to use the product rule on this because I have something that depends on s times something that depends on s. So I've got this minus sign that I don't want to forget. But I could use the product rule to have, well, the derivative of s squared is 2s times y of s. And then I would have plus s squared times the derivative of y prime. Okay, so now this is capital Y derivative. We haven't seen one of these appear in any of the problems we've solved so far. So up until now, it's been take the Laplace transform of both sides and then solve for y of s. Well, here we're going to have some y primes floating around, so let's just be aware of that. Then I've got s times y of 0. Y of 0 was 2 minus y prime, which was minus 1. What am I doing? Sorry. I'm taking the derivative of this. So taking the derivative of this piece here with respect to s would just give me y of 0, right? Because that's a constant. And then taking the derivative of y prime with respect to s, y prime of 0 is a constant. So its derivative would be 0 with respect to s. And this value we get from there. Any questions? Okay, so then I'm moving on to the next term. Let's see, we would take the derivative of this. So again, we have a product rule where I would get 1 times capital Y of s plus s times y prime of s. And then taking the derivative of y of 0 again would give me 0 with respect to s. Okay, so now we're going to group things together. So we're going to group our y and our y primes together. We've got y's and y primes to keep track of. So let me distribute this negative sign down here. And then let me plug in the fact that y of 0 was 2. So I get a negative times a negative. That gives me plus 2. Okay, any questions? Okay, so now let's group our terms together. So in other words, I'm going to group all of my y's together. Those three, and I'm going to group my y primes together. So let's see. Just here and here, and I'm going to move everything else over to the other side. So that means I'm going to move the 2 over to the other side. And so what's left if I group my y primes, I have a minus s squared and a plus s. And if I group my y's together, right, I've got minus 2s, and I've got a 1, and I've got a 1. Sorry, forgot about my delay. Okay, that works too. Okay, so there are 3 of our y terms. We can group some of these together shortly. And then on the other side, I'm going to just subtract the 2. And then I'll just note that it might be nicer just to write those two things as a single fraction. Okay, so we've got and I guess I should put my so now I've got an equation like this, and the goal here is still in step 2. I guess we're about in there. Right, is to solve for y of s, capital Y of s, and then the last step is going to be to do the inverse Laplace transform. Any ideas how we could solve for y of s here?
Integrating factor?
Exactly right. Yes, we would need to use the integrating factor on this. This is a differential equation that looks like we have kind of different notation here, but if I were to rewrite this as like x prime times right? We've got capital Y's and S's instead of X's and T's, but this is a linear first order differential equation since it has this form over here. So we're going to use this method of integrating factor. Okay, so definitely be sure that you review that process, although that technically was not in this chapter on Laplace transforms. We certainly did do this earlier in the semester. So remember that when you're going to try and use this integrating factor, the very first thing you need to do is to divide both sides by the thing in front of the first term, right? So I want to divide everything by minus s squared plus s. So I'm going to divide everything by that minus s squared plus s. And then we'll simplify since we can reduce these things a little bit. So let's see, I think that one. Reduces to 2 over s. That's right, we can cancel out a factor of s minus 1. And then on the other side, what's left is 2 over s squared. Okay, that's basically just from reducing those fractions. We've hit page 100 for the semester, in case you're wondering. It's a good milestone. 23 worksheets, 100 pages of problems. Okay, any questions?
how'd you get 2 over s?
So let's see. If it's 2 over s, you mean over for this one over here?
Really, just both of them. I'm confused.
Yeah, so if I take and factor out 2 from the top, and I factor, so now I'm looking at this one over here. I can factor out a 2, and then what's left over is minus s plus 1. And over here, I can factor out an s, and what's left over is minus s plus 1. So those factors cancel out, and that's where the 2 over s comes from. And similar cancellation for the term on the right side. Okay, and so now we've got this differential equation. And so remember how the integrating factor works. I think we call that trying to remember the notation that we used early in the semester. What did we call this thing? P of x or Q of x, or was it something else?
I think it was P.
Thank you. We'll call that P. But in any case, we're going to take the integrating factor is going to be e raised to the integral of whatever the expression is in front of the y term. And again, the point of this integrating factor is it's going to allow us to rearrange the left side so that it's the result of a product rule, and that allows us to then integrate both sides. So in this case, our mu is going to be e to the integral of 2 over s ds, which gives us e to the 2 times the natural log of s, right? We could pull out the 2. What's left over is natural log of s. And when we're doing the integrating factor, we don't need to worry about constant of integration here, right? We can pick just any integrating factor that will work. So we usually just pick one that has no arbitrary constant in it. And just keep in mind that this actually does not give us 2s. But this actually gives us s squared. And so now what I do is I take this integrating factor and multiply both sides of the equation by the integrating factor. So when I multiply everything by s squared, that's what we get. And now you can see that the nice part about this expression is now that left side actually is just what we would get if we took the derivative of y times the integrating factor. And so now we can integrate both sides. With respect to s now. And so that product rule on the left side is what allows us now to just say, well, when I integrate the left side, we're going to undo that derivative. And then on the right side, we'll get 2s plus c. So when we solve for y, that gives us 2 over, we would need to divide everything by s squared, including that arbitrary constant that we have now, the c. So this would be kind of step 2. We just solved for y of s. Now that involved doing an integrating factor problem. So any questions about that? So just to kind of go back through this before we complete it, there were a couple of things that were different about this one than the others. I mean, we're doing the same process. We take the Laplace transform of both sides. We just needed to use property L5 whenever we had those t's in front of it. And so property L5 requires us to do some derivatives. So be really careful about what you're treating as the variable and what you're treating as constants. We're taking the derivative with respect to s when you do that. And so that means you're going to have some y primes in that are going to come out of the product rule. And so now when you group things, you're going to have y primes to group together in addition to y's, and then all of the things that don't have y's. So in this case, you should be left with something that you can solve for y using an integrating factor. And that's what we did over here. And so then last step is to take the inverse Laplace transform. So step 2 was quite a bit uglier in this example, but what's left is something that actually is not too bad to now take the inverse Laplace transform of. Since I know that 2 over s, its inverse Laplace transform is 2. I can pull out that constant c. We can think about what we're going to have to do with that in a second. But for now, we'll just leave it in there. So that gives us, sorry, I forgot my c. That y of t is 2 plus c of t, doing each of those inverse Laplace transforms. We shouldn't have a c in our answer, since we have initial conditions. So how can we figure out what the value of c needs to be?
Plug in our initial conditions and solve for c.
Yeah, so we were told that y of 0 was 2, and y prime of 0 was minus 1. So using the initial condition y of 0 equals 2, that doesn't tell me anything about the value of c. So this checks out no matter what the value of c is. But checking the derivative, we take y prime, we would get c, right? And if y prime of, so let me just say, general, the formula would be c, and since we have y prime of 0, it's minus 1, that tells us that c should be minus 1. So now we've got the solution to that initial value problem, which involved an integrating factor solution somewhere in the midst of that process. So when you're working on these sorts of problems, that's something you should anticipate that you're going to have to do at some point. So something like this would definitely be you know, as tricky as it gets as far as using this method for solving differential equations. So definitely practice some of those. I think we can go back and check the tape. I think that probably took me about 30 minutes of just narrating through that process. So certainly talking slows down a little bit, but yeah, just kind of respect the amount of work that's involved in those. Are there any questions?
Say it's not t times a y prime or y double prime, but what if it's e raised to the at, where the integrating factor changed, so s is s minus a?
Yeah, so let me make sure I'm on there. So if I had a problem, let me just tweak this one. So let's say I had like something like that is what you're suggesting?
Yes.
Okay, yeah, so you do the same sort of thing. Let's see if we can do this actually. So yeah, so what this would tell us is that this is going to equal, we have to be careful here. So if we call like capital G of S, which would be the Laplace transform of y double prime, oops. That's a multiplication there, right? So we would have like the S squared, ys minus S times y0 minus y prime of 0. So in other words, if I simplify that, right, it would look like this, S squared y of S minus 3. And so the relation between this and what we did above is this is a shift of that 3 units to the right. So I can go ahead and take this. So it would look like S minus 3 squared times y of S minus 3 minus 3. So that would be what you would get for the Laplace transform of that one. And then you would have to kind of fit things in the other way. I'm not going to ask you something like that, but that's how you would account for it. At most,
But when
you'll have our powers of t when we're doing this. So at most, you might have a t squared there. And if you have a t squared, then just remember that that would mean rather than taking the first derivative, you would need to take the second derivative of that when you have a power there. And I did catch a question. Well, I missed a couple. So there was a question about, let me see if I can catch up to where that was. So I think this was a question that you had, Kenneth, so you can correct me if I'm wrong. But the question was, well, when we multiply the integrating factor, what happened to y of 2s?
Yeah, right there.
So this is actually like not y evaluated at 2s, but it's y times 2s. So kind of we took this and so this expression over here is actually what you would get if you wrote out the derivative of s squared times y prime. Right, so s squared times y prime would give us the derivative of one of the functions times the second plus the derivative of the second function times the first. So that matches up with that.
Gotcha. Okay,
Yeah.
thank you.
Yeah, so the whole trick is that integrating factor allows us to take this sum and write it as the derivative of a product. Yeah. Let's see. There was another question from earlier. Yes, I see. So Austin asked earlier, I had things written out like this. I had a 35 over here and a 25 over here. That's not good. So let me just double check. I believe that all of those should be 25, sorry. I think I just wrote the wrong value there. Thanks. Any other questions about this example? I will put up solutions for this last one here. I'll just say, if you want to work on it now and give it a shot, if you've already started it, I'll stick around. I think I'll end kind of my presentation for the day, so I can kind of stick around and use the final 50 minutes for office hours if you have any questions about homework related things. Or I would suggest giving E a shot. And if you have any questions working on this one, I'll stick around. Happy to answer any of the questions that you have. But yeah, definitely don't forget about your homework that is due tonight. And then on Wednesday, we'll just get ready for the last exam. And yeah, if you are done taking a break from differential equations, please fill out the FCQ. Should take only 5-10 minutes to go through those. That feedback again is really important to us. But otherwise, I'll just stick around here, and if you've got any questions about anything we talked about today or anything at all, I can stick around Zoom. You can chat them into me. We can talk with each other. Otherwise, yeah, have a nice afternoon and good luck finishing up your homework. And I'll see you guys on Wednesday.